Good day. I am Jemima Bian Anila, and I will be discussing two papers related to autonomous driving. The first paper is Multi-View 3D Object Detection Network for Autonomous Driving by Chen et al. From Tsinghua University and Baidu Inc. Why use multi-view for 3D object detection? For a self-driving car to navigate, it needs to know more than just a flat box around the car on a screen. It needs to know exactly where that car is in 3D space. The challenge is that different sensors give different types of information. For example, LiDAR gives accurate depth but less semantic detail, while cameras give rich visual details for segmentation, but poor depth. Existing methods try to fuse these modalities for 3D tasks, but they often struggle or fail. So how do we combine this data effectively for object detection? The key concept in their methodology is having multiple views of the same input. The views are bird's eye view, front view, and image view. Why is multiple views needed? Each of these views captures different information. The same object looks different in three different views. The bird's eye view shows position and layout. The front view shows height and depth, while the image view shows appearance and texture. The full pipeline. Their proposed pipeline consists of two networks, the 3D Proposal Network and the Region-Based Fusion Network. LiDAR and camera for different views. The network takes the LiDAR point cloud and RGB image as input. It encodes this information into the bird's eye view, front view, and image view. 3D proposals using bird's eye view. The algorithm first looks at the bird's eye view to quickly find candidate boxes or potential 3D regions where the objects might be. Why bird's eye view? Because objects are much easier to separate from above because they don't overlap as they do from a front camera view. Proposal projection into different views. Once we have these 3D proposals, we project them onto the feature map of all three views, BV, front view, and RGB image. Key innovation, deep interaction across views. The region-based fusion network refines these proposals and predicts the final 3D bounding boxes. Notice that instead of just combining the final answers early or late, they fuse the features deeply across the layers, allowing the different views to talk to each other in the middle layers. This leads to more accurate detection. Object class and precise 3D box prediction. The fused features go through a multi-class classifier and a 3D box regressor. These helps answer the questions, what is the object and where is this object exactly? Results, 3D bounding boxes. This approach results into more accurate 3D localizations, sizes, and orientation of objects compared with stereo-based method 3DOP and the LiDAR-based method VeloFCN. If we zoom into the bounding box of the white vans here at the bottom image, we see it was not captured by 3DOP. VeloFCN cut the obstructed van here, but the methodology of MV3D was able to capture and segment the full outline of the vans. Results: 3D localization and detection. They tested the model on the Kitty benchmark, which is the industry standard for autonomous driving. MV3D outperformed previous state-of-the-art methods by 25 to 30% in 3D localization and detection. Results: recall versus intersections over unions. With just 300 proposals, it achieved a 91% recall at a strict 0.5 IOU threshold, while previous methods achieved only around 40 to 50%. Using only 300 proposals, the approach obtains 99.1% recall at IOU threshold of 0.25 and 91% recall at IOU threshold of 0.5. In summary, by converting 3D data into multiple views and fusing them deeply across layers, more accurate 3D object detection can be achieved. Recommendations are the following. LiDAR is expensive and not always available. Multi-branch architecture is complex. Future work could focus on making it faster for real-time hardware. Further exploration of multimodal complementarity is a key path forward. The second paper is End-to-End Learning of Driving Models from Large-Scale Video Datasets by Xu et al. From University of California, Berkeley. This paper takes a very different approach from the first paper. Instead of detecting objects first, it tries to directly predict driving actions from video. Why learn driving behavior from video? Perception action models are complex. They need training data with diverse visual appearances and realistic behaviors. Most driving models are trained in small simulations or in situ from a single vehicle. So what happens if we place this model into a new car in a new environment? They will not generalize well. This brings us the question, can driving behavior be learned directly from video? To answer this question, they first had to create a dataset called Berkeley Deep Drive Video. It contains over 10,000 hours of driving dashcam video streams from different locations in the world. It also comes with GPS, IMU, gyroscope, and magnetometer readings of smartphones. It covers various driving scenes and lighting conditions. The dataset as shown is 2 orders of magnitude larger than existing benchmarks like KT or Cityscapes. This massive diverse dataset will help create a generic driving model that can generalize across different visual appearances and realistic driving behaviors. The end-to-end model. The model first takes current video frames and previous vehicle motion such as speed, steering, etc. Then it uses an FCN LSTM network. The fully convolutional network, or FCN, sees the scene, and the long short-term memory, or LSTM, remembers the history of the car's motion. The CNN extracts the visual features while the LSTM processes these features over time to understand motion and context. Finally, the model predicts future and driving actions. Here are some unique characteristics of their model. It remembers past information. Its decision depends on history like previous frames and motion. It doesn't depend on just a single frame of the current video. It also doesn't just predict one action. It can output probabilities. For example, 60% to go straight, 30% stop. This is useful because in real driving, there are often multiple valid actions. Privilege training, a side task. This side task helps the model learn a much better internal representation of the world. Results. Discrete and continuous actions. The image on the left shows the discrete actions predicted by their FCN LSTM model. Straight at the top, slow or stop, turn left, and turn right. The color intensity shows the probability value. In sub-figure A and B, the car is going through an intersection. The model predicted to go straight when the light is yellow as seen here, and the prediction changes to stop when the traffic light is red, indicated by the higher intensity here. This indicates that the model has learned how human drivers often react to traffic light colors. In the second pair, the car is approaching a stopped car in the front. In C, there's still empty space ahead, and the model predicts to go or stop roughly equally. However, when the driver moves closer to the front car, the model predicts stop instead. This shows that the model has learned the concept of distance and automatically mapped it to the feasible driving action. Now for continuous actions, the green sector with different darkness shows the probability map of going to a particular direction. The blue line shows the driver's action. We can see that it approximates well the possible actions according to what it sees. The action is turning left when the lane goes left and vice versa. Results on the privilege training. In the first column of images, there is a red light far ahead in the intersection. The privilege training approach has successfully identified that and predicted stop in C, while the other 2 methods fail and still predict to keep going straight. In summary, using deep learning, driving behavior can be learned and predicted from video and past motions. Large datasets and auxiliary tasks like segmentation improves performance. Recommendations are the following. To close the loop. The current model only predicts what would happen in a video. Future work needs to test it by actually controlling a car in real time. Multi-sensor fusion. This study focused on monocular cameras. Integrating LiDAR data like the MV3D paper earlier would likely improve safety and depth perception. That is the end of the presentation. Thank you for listening.